We're going to do last day of regression notes, talking about coefficient of determination. So first we're going to start by showing you some formulas on your formula sheet, on the AP formula sheet. Pull up that formula sheet, make sure that you know where they are located. What's nice is you don't need to memorize them. You just need to know what the variables actually represent. So let's look at this first problem. It says the following statistics are found for the variables posted speed limit and the average number of accidents. So we have here some summary statistics. X bar is the average of X's equals 40. Y bar is the average of Y's equals 18. SX is your standard deviation of X's, 11.6. And SY is your standard deviation of Y is 8.4. And your R equals 0.9981, your correlation coefficient. So utilizing these, we need to find the least squares regression line and predict the number of accidents for a posted speed limit of 50. Well, before, when we found the least squares regression line, we needed the data points. We put them in the calculator listed in spreadsheets, the calculator spit it out. Well, here I don't actually have each specific data value. I only have the average of X's, average of Y's, and standard deviation. So this is when the formulas I just showed you come into handy. Notice one way to write a least squares regression line is by taking B null plus B1x. Well, let's find, how do we find B1? B1 is your R value times your standard deviation of Y's divided by standard deviation of X's. And your B naught is your average of the Y's minus B1 times average of the X's. So let's find B1 first. Our R value is 0.9981. Standard deviation of Y's is 8.4 divided by standard deviation of X, 11.6. Crunch the numbers in your calculator, we get 0.723 as our slope. So to find the y-intercept, we have average of your Y is 18 minus your slope, we just calculated 0.723 times average of the X's, 40, and that gets you negative 10.92. So to write it as a least squares regression equation, y hat equals 0.723x minus 10.92. Again, we should label our variables. Again, x equals your speed limit, and y hat is your predicted number of accidents. So we read the question, we found the line of equation, least squares regression line, but we have yet to answer what is the predicted number of accidents for a posted speed limit of 50. So if we plug in 50 into there, the calculator can tell you that your predicted number of accidents is 25.23. Again, always include units. We're talking about accidents here. Data is the number, statistics is the interpretation, how it relates to the problem. So again, check your AP formula sheet, make sure you know where to access these formulas. So how do we interpret computer regression? Okay, stats in the real world is all done on computers. So how do we interpret that computer output to find our slope, our y-intercept, and our S and R squared? Okay, so Minitab is one popular one used in real world statistics. And here's what the output would look like. Notice we have two things labeled. One's labeled constant, one's labeled NEA change. So your constant, think back in math, a constant does not change. That is your y-intercept. If it's not labeled constant, it will be labeled y-intercept. Whatever is not labeled constant or y-intercept is your slope. So this relates to the problem NEA change. Negative 0.0034 deals with slope. Notice we can easily find R squared. R squared is typically going to be given as a percent. You can change that to a decimal. R squared is 0.606. We can take the square root to find R if needed as your correlation coefficient. And big S is your standard deviation of residuals. So notice on this lower half one, again, as I told you, if it's not labeled constant, it will be labeled intercept. So intercept is your y-intercept, whatever's not labeled intercept is your slope. And we're always dealing with the very first number. So let's utilize that to help us find the least squares regression line for light here. So we have this computer output. Notice constant is our y-intercept of negative 0.08259. Light, because it's not labeled constant or y-intercept, is our slope. So y hat equals, because it's predicted, 0.04464x minus 0.08259. If we wanted to find r squared would be 0.9827. We could take the square root to find r. And again, our standard deviation of the residuals would be 0.06112. So here we have some data based on age and range of motion. So one measure of the success of knee surgery and post-surgical range of motion for the knee joint following a knee dislocation. So we have some data based on age and range of motion after a knee dislocation surgery. Is there a linear relationship between age and range of motion? So if you want, you can put these in your calculator, pull up a scatter plot, check your correlation of coefficient. But remember, we can also check this by the residual plot. So here I have the residual plot for you. Remember, a residual plot is just taking your least squares regression line and putting it horizontal. And in order to tell if there is a linear relationship, we want no pattern in the residuals. Okay, that means that that middle line, that horizontal line, is halfway between the data points. Well, since there is no pattern in the residual plot, there is a linear relationship between age and range of motion. So coefficient of determination is r squared. We have a couple of formulas in order to find it. Again, these are on your AP formula sheet. You don't need to memorize them. You just need to know where to access them. So coefficient of determination is r squared, labeled r squared, and it gives the proportion of variation in y that can be attributed to an appropriate linear relationship between x and y. So normally, notice the formulas here relate to standard deviation, which again, in a way, describes how variable a data set is. So keyword with coefficient of determination is it describes the variation between your x's and y's. It remains the same no matter which variable is labeled x. Okay, so even if I swap x and y, your r will stay the same. If r stays the same, r squared stays the same. And if r squared equals exactly 1, that means that all data points are on the regression line. That means you have r squared equals 0, then there is no association between x and y, and the regression line should not be used. Okay? So the higher your r squared value, the better, just like the higher your r value. The higher your r squared value is, the higher your r value is. So the higher correlated your data is. So here we go back to our knee surgery data. And let's examine r squared. So suppose you're going to predict a future y, but you didn't know the x value. Your best guess would be the overall mean of the existing y's. So here we have a scatter plot of the data. And if we take the average of only the y values, we get 130.083. Now, if we take the residuals of that, again, distance from the regression line from each data point, and we sum those up, the sum of the squared residuals for y would be 1,564.917. Now, suppose we were going to predict a future y, but we don't know the x, but we do know the x value. Your best guess would be the point on that least squares regression line for that x value, or the y hat, the predicted. So again, if we go back to our scatter plot, again, we have now done our predicted y hat least squares regression equation. Again, if we calculate the sum of the squared residuals based on the least squares regression line, we get 1085.735. So by what percent did the sum of the squared error go down when you went from just an overall model to the regression on X? Well, we went from 1,564.9 to 1,085.7. And if we actually find that percent of increase based on this formula, we get a value of 0.3062. So what does this mean? That is your R squared. Okay, that is the amount of variation in the Y values that is explained by the X's. So you're not going to have to calculate that by hand. This is just showing you how it is calculated. Calculator will spit out the R value, which you can then square to get your R squared. So how well does age predict the range of motion after knee surgery? Approximately, using that number as a percent, 30.6% of the variation in range of motion after knee surgery can be explained by the linear regression of age and range. And again, the higher percent that is to 100, the more accurate your least squares regression is, or how correlated your X and your Y variable is. So you need to memorize. If a problem asks for interpret the coefficient of determination, this is how you answer the problem. You find the number as a percent, so something percent of variation in whatever your Y is related to the problem, like the past one was knee surgery, is accounted for by the least squares regression line relating what is your Y variable, what is your X. So in the last one, we related it to age and knee range of movement. So memorize, make a flashcard. So here we have another computer generated analysis of the knee surgery data. How do we find the equation of the least squares regression line? We need to find the slope and the y-intercept. Remember, a slope will typically be labeled something in relation to the problem, which is age. So our slope here is 0.8710. Y-intercept here is labeled constant at 107.58. So y hat equals 107.58 plus 0.8710x. So what's your correlation coefficient and the coefficient of determination? Well, we have R squared, never used R squared adjusted. R squared will get us our coefficient of determination. And we always state it as a decimal. Okay, only when you interpret do you include it as a percent. So to convert to decimal, we'd have 0.306. And if we want to find R, we then need to take the square root of 0.306 and we get 0.5532. So based on that 0.55, that would be considered a moderate positive correlation between age and range of motion. So outliers, okay, in a regression setting, an outlier is a data point with a large residual. Okay, a large residual means the distance from the predicted amount is very large. An influential point, by definition, is a point that influences where the least squares regression line is located. And if removed, it will significantly change the slope of the least squares regression line. So sometimes we can have an outlier point, but it may not actually change the least squares regression line because it actually might be on the least squares regression line. So with regards to regression, sometimes an outlier is only influential if it's going to change it. So look here, we have some more data on racket and resonance and acceleration for some balls. One factor in the development of tennis elbow is the impact-induced vibration of the racket and arm at ball contact. Okay, that's kind of how we get tennis elbow sometimes. Sketch a scatter plot of the data and calculate the least squares regression line and the correlation coefficient. So does there appear to be an influential point? And if so, if we remove it, recalculate the least squares regression line and correlation coefficient. So let's start by scatter plot. If you want to put those into your calculator, you can. Again, we're only putting in a second column and third column. But here would be the scatter plot. And notice we do have a value way out here that would be an outlier. Okay, 189.30 is very far away from the rest of the data points. But we don't know yet if it's influential. Okay, we need to remove it and recalculate the least squares regression line. So notice currently it's on this least squares regression line, but let's remove it. Notice when we take that outlier point away, notice the least squares regression line was moved. So since it was moved, that means that it is indeed an influential point. So not always are outliers going to be influential. It's only if, when you remove, it changes the least squares regression line. If it stays pretty much the same, not influential. This one was. So which of these measures are what we call resistant, i.e. they don't change no matter if you add points? Least squares regression line, correlation coefficient, coefficient of determination. None of those are resistant. They all are affected by outliers. Okay, one value can significantly change all three. Which makes sense since your correlation coefficient R is determined by R squared and vice versa, and your R squared is also determined by how closely your points are to your least squares regression line. So I cannot say this enough. Association does not imply causation. Okay, an association between an explanatory X and a response Y, even if it is very strong, is not by itself good evidence that changes in X actually cause changes in Y. So let's think of this study. Once found that people with 2 cars live longer than people who only own 1 car, and owning 3 cars is even better, and so on. So is there substantial positive correlation between the number of cars X and the length of life Y? And why? So do we really think that owning more cars is really the cause of your increased health? No, if you own more cars, you probably have more money, so you're getting better health care. You might be able to afford gym memberships, other things that would make you healthier as well. So it is not the fact that owning more cars makes you live longer. It's probably the fact that owning more cars probably means you have more money and more access to things to help you live longer. Okay, so cannot stress it enough. Correlation does not prove causation. You can only prove causation through a well-designed experiment.